This is Mrs. Young, and this lesson is going to be from our functions unit, and it's going to be reviewing lessons 1, 2, and 3. So what you want to do first is get out your functions packet. If you don't have your functions packet, it is in the Google Classroom, and you can print off the pages you need from the Google Classroom, or you could just get out some blank paper and copy down what you need on blank paper. So as we go through this review of lessons 1, 2, and 3, remember that you can pause the video, rewind the video, or rewatch the video if needed to help you out. So I'm going to start with lesson 1. And right now I'd like you to turn in your packet to page 15. So again, page 15 of your functions packet, and we're going to take notes reviewing lessons 1, 2, and 3. So starting with lesson 1, when we covered lesson 1, the topic there was on whether or not what we were looking at was a function versus not a function. How do we know if something's a function or is it not a function? There were 3 different ways we could represent this or look at this. The first thing that we did was we looked at whether the table or ordered pairs represented a function or not. Again, copying these notes down on page 15 of my packet. So if we look at a table, let's just go ahead and make a little table here as an example. Make a table of values. Again, the top row is going to be my x values and the bottom row is going to be my y values. I'm going to start with an ordered pair of -2, 0. Then I have another ordered pair of 1, 3. Another ordered pair of 4, 0. And then finally another ordered pair of 1, 3. 1, -3, sorry. So there's a table of values. Given a table of values, how can I tell if it's a function or not? Well, hopefully you remember that this one is not a function. If we look at the input value of 1, that has more than one output value. So this is an example of one that's not a function. Again, it's not a function because we have an input value of 1 that has more than one output value. Or you could say there's a repeated x value of 1. Doesn't matter that we have a repeated y value of 0. That doesn't determine whether or not it's a function. So again, looking at a table or ordered pairs, you want to see if the input has more than one output, or do you have repeated x values? The second thing that we looked at, whether or not something was a function, we looked at a graph. And when we looked at a graph, let's just go ahead and draw a graph. So I'm going to draw a little xy axis here. And I'm going to draw a graph of, let's say I have a graph of a circle. Is this circle a function, yes or no? Well, remember, if we drew a vertical line through the graph and it hit the picture in more than one spot, we said it was not a function. So again, this one is not a function because it does not pass the vertical line test. So not a function if it doesn't pass the vertical line test. And then finally, the third thing that we looked at, whether or not something was a function or not, we looked at the equation. When we looked at an equation, how could we tell if it was a function or not? I'm going to give you an example of an equation. If I had x squared plus y squared equals 3. This one is, again, not a function. What makes this not a function is the fact that we have an exponent on the y value. The fact that y is squared. Again, if it's squared or has any exponent other than 1, it's not a function. If you're still a little confused on lesson 1, you can go back in your packet and look at, I believe it was pages, I want to say 1 through 4 for more examples, or you can go back and watch the video that I posted on lesson 1. Next, when we went to lesson 2, I feel like lesson 2 was a little bit easier because lesson 2, we were comparing functions. We were comparing functions by looking at their rates of change. So when we compare our functions, we look at their rate of change. And I think what made this easier for us is that whenever we're talking about rate of change, we know that we're talking about slope. We just spent the whole prior unit talking about slope. We know that slope represents rise over run. we know that that's the same as our slope formula. Remember your slope formula? It's y2 minus y1 over x2 minus x1, which is the same as our m value. So again, those are different ways to look at slope and talk about slope. Again, when we see rise over run, we're thinking about our graph. We can make our slope triangle. If we have a table of values, we use the slope formula, y2 minus y1 over x2 minus x1. And finally, if we're looking at an equation, we want the equation to be in slope-intercept form, y equals mx plus b, y equals some number times x plus some number. That number in front of x, we call that our slope. So we can look at those different representations of slope and compare them to figure out which one has a bigger or smaller slope. Again, if you're still kind of confused on comparing functions, in your packet, you can look at pages 6 through 9. We did a bunch of examples on pages 6 through 9. And then finally, in lesson 3, we looked at whether or not our representations were linear versus nonlinear. Linear versus nonlinear. And again, we looked at 3 different representations. The first one I want to show you is the graph. I feel like this one is the easiest, right? For a graph to be linear, we want it to be a straight line. Linear line, straight line. If it's nonlinear, it's not a straight line. Could be curved, could have a bend in the line. It's not a straight line. So again, linear, straight line, nonlinear, not a straight line. I feel like it's easy when you're looking at a graph. Another representation we looked at was an equation. Again, for our equation, if we can put it in that form, y equals mx plus b, that's going to be a linear graph. We can graph that. We know that's a straight line. If it's nonlinear, then you're going to have an exponent on the x term, some exponent other than 1. Like if I had, I'll give you some examples, like if I had y equals x squared, that's not going to be linear. It's not going to be a straight line. Another example would be if I had y equals 1 over x. Remember that this would represent a negative exponent on x, so that would not be linear. And then the third representation we looked at was a table. So in our table, again, for it to be linear, we're looking for a constant rate of change. Constant rate of change. And for it to be nonlinear, there's no constant rate of change. This is a little bit harder when you're looking at a table. So I want to give you a really simple example. So let's make a little table down here. Again, we're somewhere on the bottom of page 15 probably. Let's make a table of values, x, y values in our table. So let's say that we have an ordered pair of, let's say 0, 1. Then let's say our next ordered pair is 1, 3. Then my next ordered pair is 2, 5. And then my last ordered pair, 0, 1, 2, let's say 3, 8. So I want to know from a table if this is linear or not. One thing that I'm noticing is that my x value keeps going up by 1, right? Keeps going up by 1. But if I look at my y values, if you go from 1 to 3, that goes up by 2. But if you go from 3 to 5, that also goes up by 2. So this looks good. But then when I go from 5 to 8, that's going to go up by 3. So this one is not linear because I don't have that constant rate of change in the table. So you're looking for that constant rate of change. So that's a quick review of lessons 1, 2, and 3, less than 10 minutes. Again, if you're struggling with lesson 3, you can go back in your packet, and I would say look at pages 12 and 13 for some more examples, or go back and watch that lesson 3 video if you need to. Right now, what I'd like you to do is go ahead in your packet, turn to page 14. So we're sorry, I think this is page 14. Let me double check. Because we're going to go ahead and look at that last linear versus nonlinear example and look at some practice problems. So in my packet, yeah, I'm on page 14, not 16. Sorry, guys. So again, look at page 14. and we have some examples here. So what I want you to do is take a few minutes for each one and tell me if it's linear or not linear. You don't even have to explain, just is it linear or not? I'm going to do the first one with you as an example. If I go from 4 to 8, that goes up by 4. If I go from negative 11.2 to negative 26.4, I'm going to have to pull out my calculator. So I pull out my calculator and subtract those two values to see what I come up with for their difference. So when I subtract them, I get negative 15.2. So this went down 15.2. If I go from 8 to 12, that again goes up by 4. 12 minus 8 is 4. And then subtracting those y values again, it's still going down 15.2. Checking my last set of points, 12 to 16, that goes up 4. And subtracting my last y values, again, I get negative 15.2. So again, notice you have that constant rate of change. So because of that, we would say that this graph is linear. So I'd like you to look at the next 8 up through I and just say, is it linear or not linear? And then down at the bottom, write down on the left side which ones were linear, the letter A, B, C. So again, A was linear. So down here, I'm going to write A down here at the bottom. So then write down A through I at the bottom, either on the left side or right side, whether they're linear or not. So what I'd like you to do is go ahead and pause the video right now. Go ahead, pause it, and complete this page. And then come back and check your answers with me. So again, pause. So here are my answers. Letter B, I said it was not linear. You can tell because you have the exponent on x. C is definitely linear. That's a straight line. D is linear because it's in that slope-intercept form. There just is no y-intercept. Letter E, I can see here the x went up by 2, the y went up by 8, but then the x went up by 2 and the y went up by 16. That's nonlinear. F, also nonlinear. Again, the x in the exponent represents a negative exponent. Sorry, the x in the denominator represents a negative exponent. Letter G, not a straight line, so that's nonlinear. H is linear. There's no exponent on x. And then letter I said was nonlinear. Again, here the x went up by 1, the y went down by 10, but then the x went up by 2 and the y went down by 5. So it wasn't going in a regular pattern. So we don't have that constant rate of change. So down at the bottom under linear, you should have A, C, D, and H. And then under nonlinear, you should have B, E, F, G, and I. So again, once you check these over, if you're struggling, this was from this page right here was from lesson 3. If you're having a hard time with that, go back and rewatch the video for lesson 3 or 2 or 1, or look back through your packet. So again, this was a quick review of lessons 1, 2, and 3.